Hey guys, so just one phase today, integrals in particle motion. Okay, so the particle motion stuff, guys, is basically the physics stuff. So you want to be acquainted with Susan's table, the physics version. Well, actually both, but the physics version will come into play. So a particle moves along the x-axis so that at any time t, its position is given by x of t, velocity is given by v of t, and acceleration is given by a of t. And just remember that velocity is the first derivative of position, and acceleration is the second derivative. So if at any point in this phase you see x prime or x double prime, that translates to velocity and acceleration. Okay, now we've got three formulas here that we're going to use. And okay, so I'll show you them and then I'll try to do a little demonstration. So the net change in position from t equals a to t equals b, this is also known as displacement for those of you who are in physics, is given by the integral from a to b of velocity. Okay, that will give you the net change in position. And by net change, guys, I'll explain that in just a second. Total distance traveled from time A to B is given by this integral, where you do the absolute value of velocity. And then the position of a particle at time t equals b is given by this formula. So x of a is the position of x at time A. I'm just making a video. Okay, that's given by the position. So x of a is the position of the particle at time A. And then you add on to it the integral starting at this time A. So the input on x and this lower limit of integration need to be the same. And yeah, and if you think of this, guys, so x of a, that's the position of the particle at time A. And then this here, that is the net change in position. So you start out at this position and then this, and then you add on the change in position, and then that gives you the position at time B. Okay, so let me just do a little demonstration. Okay, so if I've got this graph here of velocity, let's say this is the velocity graph, it's constant, 8 miles per hour. And I want to know, so I want to know the change in position. So the change in position from t equals 4 to t equals 9. So we could think about it, guys. How many hours between 4 and 9? That's 5 hours. So if you travel for 5 hours at 8 miles per hour in a positive direction, so you travel for 5 hours at 8 miles per hour, that would be 40 miles. Okay, that'd be 40 miles. But now if you look at it from like an area under the curve perspective, if you go like this, what is this? What's the area under that curve there? It's 40. Okay, that's the base is 5, and then the height is 8. So that would be the integral from 4 to 9 of the velocity. Okay, gives you 4. So the area under a velocity curve tells you the change in position. Wherever we were at, so I'm not sure how many miles we had already traveled at time t equals 4, but we had traveled, 40 additional miles. Yeah, okay, so let's go down here for a second. So if we see something like this, so let's figure out here the change in position from 4 to 9. So the change in position from 4 to 9 here. So from 4 to 5, so this is the velocity curve. From 4 to 5, we've traveled 9 units. And then from 5 to 9, we've traveled 12 units, but in the opposite direction. So this is 9 minus 12. So the net change in position is -3. So the net change in position there would be -3. Now by net change, I mean that like there are some changes that counteract each other. So so net change is different than total distance traveled. All right, so down here, this would be total distance traveled. I'd have to take the absolute value of this graph, which would flip over the negative parts. And then the net change from 4 to 9 would be 9 plus 12, would be 21. Okay, so this is net change versus total distance. Yeah. All right, so now let's jump into this. Oh, where did it go? Where did this thing I was writing on go? I'll find it. Oh my gosh. Don't even tell. Here it is. Oh my God. Okay. Marisa and Laura are here with me. They got to witness that. So, okay, now, before we jump into it, let me show you this. This won't be long. We're just going to do these examples in a minute where we're interpreting these integrals. Okay, so average velocity I've got to talk about. So guys, the average velocity formula is this, and I'm going to show you why it is. Okay, 1 over b minus a, the integral from a to b, and then velocity. Okay, so in this box, I'm just going to show you why this is the average velocity formula. And remember that v of t is x prime. Okay, so let's use the fundamental theorem of calculus. So I'll just bring down the 1 over b minus a, because that's a constant. And then I'm using the fundamental theorem of calculus here, which tells us to do, you know, the brackets, and then these endpoints move over here. But what goes inside the brackets? The antiderivative of velocity. Now remember, velocity is x prime. So what's the antiderivative of x prime? It would just be x. Okay. And then I could do this thing where we plug in the top one minus plug in the bottom one. X of b minus x of a all over b minus a. And guys, this should look familiar. This is the average rate of change. That's the average rate of change. And in this case, our rate of change is velocity. So this is average velocity. All right. So average velocity formula is this, or you could write it as this, from a to b, b of t dt all over b minus a. So you could write the constant out front as a denominator. Alrighty. Okay. Now just a couple more things, and then we'll get into the examples. So the average acceleration from t equals a to t equals b, guys, this average formula, this average velocity formula, you could use it to find the average of anything. Whatever you want the average of, you just put as the input of the integral. So if I want average acceleration instead of velocity, I would just go 1 over b minus a, the integral from a to b, acceleration. If I wanted the average speed, remember guys, the speed at any time t is the absolute value of the velocity. So if I want the average speed, I would go 1 over b minus a, the integral from a to b, and then I'd plug in the absolute value of velocity. Okay, now I know already it's kind of been a long video, but these are going to go really fast. I just had to get that stuff out of the way. So interpret each integral expression in words. So you have to match these to what you see on this page, basically. All right, this first one. This, when you just see a straight up integral of velocity, that's change in position. So that's change the particle's position from t equals 0 to t equals 5, right? Now this one, you got to match it to, one of the formulas on the other page. Guys, the integral of the absolute value of velocity, that's total distance. Total distance traveled from t equals 1 to t equals 6. This one, when you have like a function value, like a position value added on to an integral of velocity, just check and make sure that this input is the same as that lower limit, all right? And it has to be plus. And then this is going to give you the position of particle at t equals 12. Okay. Because you're just adding on the net change to the initial position. That's going to give you the position of the particle at the end of the interval. All right, now this one here, if you've got like a fractional coefficient out front of the integral, you just got to check one thing. Is this, all right, so this is A, this is B, is this B minus A? The answer is yes. Okay, so then you know that you're dealing with average. Okay, so it's the average blank from t equals 0 to t equals 5. Guys, the answer to what goes in this blank is whatever is being represented as the input of the integral. What is x prime? So this is the average of x prime, but in this context, x prime is velocity. All right, we just got two more. Okay, this one. This is kind of a similar situation. Instead of having a constant multiple out here, that's a fraction, like 1 over something, we just have, this over 2. So you could rewrite this if you wanted. You could go rewrite that as 1/2, 11 to 13, e of t dt. All right, so this is A, this is B. Is that B minus A, 13 minus 11? Yes, it is. So this, again, this is average. And then you ask yourself, what is the input of this integral? What is the absolute value of velocity? It's speed. So average speed from t equals 11 to t equals 13. And then this one. All right, if I let this be A, that be B, is that B minus A, 10 minus 7? Yes. So this is the average. Whatever this thing is, what does this represent? X double prime, that's acceleration. Average acceleration from t equals 7 to t equals 10.